Right, can you guys see like what I'm sharing?
Yeah.
And can you see my little arrow?
Yes.
Yes.
Awesome. Okay, that's all the technology we're gonna need.
And if this
All
turns
right,
around and
so
winds up being a super spreader event because a bunch of people are now on the streets trying to get their kids tested, you will feel this moment. You will remember it and you will regret it. Thank you.
is this?
I'm gonna try to mute everyone.
Thank you. The next seat.
All right. Okay, good. All right, so generally I don't believe in conspiracy theories, but I want to tell you about a conspiracy that actually worked. Um, please mute yourself if you're out there. So, so I'm not a historian, I'm a scientist. And so my thinking about this and why I think it's an interesting story to tell has to do very much with basically the idea that, we are a society which very often encounters problems which are, say, at the interface of science, technology, and the greater society. So there's many problems in our world right now, which kind of are of this type. Obviously we're facing a pandemic, climate change. So there's some kids out there that are drawing on my transparencies, but okay. that's cute. Anyway, so and one of the things that interests me is precisely this sort of situation, this interface. And it's interesting to look at what happened in the past and how scientists and society dealt with a challenge, right? So there are two kind of facets for that. The first is just trying to understand what was in the mind of the scientists. Like, how did they view their relation to the society that they were in? How did they think of the technology or the science that they were developing? What were the kinds of, let's say, responsibilities that they felt towards the society? And the other part of it is, the flip side. What did the society think? What did the governments think about the science? How did they react to the information that the scientists were telling them? How did they incorporate that information? And finally, another part of the story, which I think is very interesting, especially kind of as you talked about science to the lay public, is just the process of science itself. So, sometimes we're taught in school like something called the scientific method, right? And the scientific method is, well, you have some thesis or some idea that you want to check. You then go out and you have an experiment and you check this idea, and then the idea is either confirmed or not. And that's kind of very often what we get taught in school. And that's just a load of crap. That's not at all how science happens. It's kind of fairly complicated process. And so, one of the reasons to tell the story that I'm about to tell you is to show you kind of what happens in real time. Like, how is it that scientists make decisions? How do they face uncertainty? Because very often, if you don't understand the way science works, it causes, again, a lack of communication between scientists and society. So that's kind of the motivation for this story. Now, the way that it's gonna go down is there's basically two parts. The first part I'd call very roughly character development. So we're gonna like meet the various personalities that are going to be playing a role here. And maybe that'll take me, I don't know, depends on questions. By the way, you can feel free to interrupt me with questions at any point or comments or whatever. This is pretty informal. So, and after we're done with the character development, then we'll just take a break. We adjust our level of substances. And then what happens is then the second part will start, which is more like kind of direct plot.
Yo, Ami,
There's like
tell Lana,
like two mics.
tell Lana to turn to mute her Zoom.
Yeah, turn it off.
You have to mute.
All right.
Sorry.
Yep. Okay, cool. All right, so let's start. Unless there are any comments, questions, something. All right. So here's where our story starts. It starts in Hungary. This is, of course, the map of Europe today, but back in when our story starts, the map was very different. It was the era of various empires, and in particular, Hungary was part of the Austro-Hungarian Empire. So the characters, the first set of characters that we will kind of meet are the so-called Martians of Hungary. So who are the Martians? The Martians essentially are scientists who are born like in Hungary around 1900. Let me turn off a bunch of these phones and devices. All right, good. And there's a whole set of them. So around 1900, wait, something's happening. Kill Facebook. Facebook bad. There we go. All right. Good. So there are a bunch of scientists that are born around in Hungary around 1900. They have the C, who is like a very famous chemist, von Karman. He's an aviator. Von Neumann, who essentially contributed to every freaking science. He had important contributions to physics, to math, computer science. He invented a lot of information science. And Leo Szilard, who is going to be kind of our first character, is among them. Also, Teller and Wigner. And just to mention another peculiar character who's not really going to be part of our story, but one of the most famous mathematicians of all time, Paul Erdős. He was a crazy ass dude. He wrote, I think, maybe something like 1,500 papers. His entire life was consumed by math. He just kind of basically did math nonstop and just drank coffee and took Ritalin to be able to produce more and more results. So he was very, extreme, like to the point that almost everybody collaborated with him during his life. I just found this quote kind of cute because you could just change the wording a little bit and it would apply today. You could just say social media is something the Russians invented to destroy American democracy. So it's pretty close to what he was saying, keeping with the spirit. And there are 4 or 5 others. So it's kind of bizarre and amazing that so many distinguished scientists appeared, in what was not the center of the universe. I mean, this was not like the most important country ever. Also, so for example, Wigner and Debussy had got Nobel Prizes. I mean, so these are really quite distinguished people. So something strange happened and a joke developed because it was so bizarre that so many different scientists affecting essentially all of scientific work appeared around 1900, that there was a joke developed that the most likely these were the children of aliens, that is Martians. So the idea was that what really happened is that Martians landed somewhere in Hungary and were able to sort of generate this crazy level of intelligence. But it's kind of interesting to ask, who were these people? Because some of them will play a very important role in our story. And all of them were actually Jews. They were all Jews educated in Budapest, which at the time was 23% Jewish or so. Some of them came from families who were ennobled. So they were kind of, if you want, the upper middle class or the bourgeoisie of Hungary. Some of them kind of became part of the kind of official aristocracy because they were children of distinguished business people. And so they formed kind of the middle class of Hungary to a very large extent. So in 1910, Jews were just 5% of the population of Hungary. but there were 60% of all the merchants, there were 60% of all the book printers, 40% of all innkeepers, 50% of all doctors. And, you know, as far as the education level, gymnasium or kind of high school was considered sort of fairly advanced education. Not everyone got that education at that time. Of course, even fewer people went to college. So it was quite remarkable that so many of them were educated. And okay, so why did this happen? Well, it ain't because Jews are magic. It's just because there was an aristocracy in Hungary, and that aristocracy just didn't care for certain professions. And at the same time, 30% of the population was illiterate. So there was just this kind of gap in, you know, various professions. And it so happened that Jews who sort of lived in various villages around Budapest moved into the Budapest during the 19th century and, you know, began to take part in this economic activity and in fact, essentially filled out the middle class. And this, of course, includes our first character, Leo Szilard. So what happened to Leo Szilard is this: in 1914, of course, World War I begins. And because Szilard had an education, he went to gymnasium, when he went to high school, basically. He was considered not a simple soldier, but he was being sort of get ready to be made an officer in the cavalry. So in the Austro-Hungarian Prussian cavalry. And, you know, he was about to be deployed with his regiment when the first connection happened that with an event that affects us today. Szilard gets the Spanish flu. So Szilard gets the Spanish flu, and, you know, he shows up and asks the officers not to send him away. And he goes with a fever and basically takes a week or two to recover. Meanwhile, his regiment is sent into war and many of them die. In fact, most of them die. So in a sense, the Spanish flu saved Szilard. But then, you know, the war ends and, you know, additional tragedy, I guess, befalls the middle class, if you like, of Budapest. First, in 1919, there's a communist revolution in Hungary, right? So people flood the streets in Budapest. There's like a lot of passion for revolt, and a government is set up by these people here. In charge is this guy, Kun Bela. And this government doesn't last for very long. So the communist revolution isn't very successful. It lasts something like 3 or 4 months. And then it essentially collapses when, in fact, a right-wing nationalist comes to power. So very quickly, the right-wing nationalists come to power. They're dissatisfied with what the communists were doing. They're very angry. They march in and they're very violent. So during the takeover of Hungary by the nationalists, about thousands of people are killed during what's called the White Terror. And again, as is familiar to all of us who know anything about the history of Russia, many Jews, of course, are part of the communist revolution, including the leader, Bela Kun. And, you know, so very quickly, the violence that is associated with being anti-communist also becomes anti-Semitic. So Jews are killed. Again, there's strife. And once the right-wing leadership seizes power, this anti-Semitic kind of part gains control. And the people in charge are unhappy that so many Jews are part of this elite class. And so they set up anti-Semitic quotas on Jews, both in schools and in universities. So effectively, though there was this sort of Jewish bourgeoisie that existed fairly calmly for many years, they see all this turbulence and collapse. And all of the people that we call the Martians, these scientists, they're all young men at the time, and they see their families in strife, and they learn very quickly that, you know, you could have sort of a nice bourgeois life one day and then shit hits the fan another day. And so this lesson is something that they're going to take with them. But in practical terms, they're obviously not going to stay in Hungary, because of the various quotas. They want to seek kind of their success elsewhere, and they go to Germany. So all of the Martians go to Germany. So why Germany? So let me tell you a little bit about Germany and sort of in the sense where it stood at the time that they made this decision. So it all starts actually in a kind of funny way by this British guy who invents a new kind of color. So it's called Movine. It's the first artificial dye. His name was Henry Perkin. And he invented by accident, completely by accident, what he was trying to do, in fact, is he was trying to help the colonials defeat malaria. But he wasn't able to find the medicine. He wasn't able to find the cure for malaria, but accidentally he discovered how to make artificial dyes, like artificial colors. So you have to remember, of course, that for thousands of years of human evolution, all the colors that people had were the kinds of stuff they found around, like various powders that they could mix and so on. So suddenly he was able to develop a kind of color that didn't exist before, and it became all the rage in Europe. So, for example, here's Queen Victoria wearing this kind of Movine. It's a kind of a purplish color. And he was trying to get the Brits to be excited about this, but chemistry was not yet a thing at that time. And the Brits were already full of themselves that they have this awesome empire and the Industrial Revolution, blah, blah, blah. So they didn't really seize the opportunity associated with developing dyes. But the Germans did. And so Germany gets very heavily into the dye business and develops essentially modern chemistry in the late 1800s. So by experimenting with various chemicals, they make more and more and more dyes. They make a shitload of money on these dyes, and that makes them better and better at chemistry. So it's kind of a cycle, right? So they become very rich on the various artificial colors that they invent that haven't ever been seen before. And along the lines kind of note, they come up with a process for making nitrogen fertilizer, right, for growing crops. So they become also rich just because they now have a new way of making fertilizer. Whereas before, what they had to do is they had to import like ammonia and import the ingredients from this fertilizer from other countries, like for instance from Chile. But another interesting byproduct of the fact that they came up with this artificial process for making nitrogen is that they also figure out a way of making explosives. So the same nitrogen process is actually important for making explosives like TNT. And in fact, one of the things that kept World War I going is precisely the fact that they were able to create this chemical process to make explosives, because the Brits blockaded Chile, and they weren't able to anymore get ammonia from Chile. And instead, they would have just run out of ingredients to make explosives, and then World War I would have ended within a year or two. Except that, of course, because of their chemical prowess, they were able to make explosives with this new process, and the war lasted until, for 4 years. So by 1920, which is when our characters, the Martians, make their decisions, Germany has got basically the best chemists in the world. And then another thing hits, which is that there's a revolution in physics called quantum mechanics. Of course, I can't take the time to fully explain what quantum mechanics is here. But let me just make a few comments just to set the stage. So quantum mechanics is essentially the core language of nature. It's what the fundamental laws of nature are written in terms of. Curiously, it's kind of a language very similar to programming. So in some sense, it's written in the language of code. It's a language of data manipulation. Typically applies to very small things like atoms, which is why it was kind of natural for Germany to get involved with this science as well. because they were very good chemists, and they were constantly thinking about elements and various manipulations of those. Very roughly, what happens in quantum mechanics is that one of the first things that people understood is the way that atoms interact with light. So for example, if you have a hydrogen atom, here you see a picture of a hydrogen atom. This is what we call an electron cloud. So this is like a single electron. And this single electron takes the shape of this blob. And if you hit it with light, then it changes its shape. It goes from this sort of blob to this kind of dumbbell kind of shape. And you hit it again with light, it again changes shape. So these transitions are associated with some very particular frequency of light. And so that was actually one of the main insights of quantum mechanics, is that, light has different frequency, has different colors or wavelengths, right? So you can think of the wavelength of light, and you can associate the wavelength of light to various colors. Some wavelengths of light are associated with visible light, some of them with radio waves, and so on. But what quantum mechanics said, which was very radical, is that in fact the color is related to the energy of the light fundamentally. And so, just to give you a sense of how important that is in your life, I mean, energy is essentially the universal currency of nature, right? Energy is never created or destroyed. In any physical process, energy just changes form from one thing to another. And so by linking energy to color, what quantum mechanics was saying is that processes of different energy are associated with, for example, the emission of light of different colors. And so when you look at objects around you, like, and you see red or you see blue, this is having to do with the energy associated with the transformations that generates those colors. So kind of this is the basics, maybe the basics of quantum mechanics. So any questions, by the way, about anything that I've told you so far?
No, this is great, Amy. We're really enjoying it.
All right. Groove on then. Okay, so just final sort of plug to say the obvious is that, the very devices that we're using now would just be impossible with quantum mechanics. Lasers, computers, LEDs, solar panels, those are all, technologies that result directly from our understanding of quantum mechanics. Now, historically, what's important to understand is that quantum mechanics was really invented mostly by German-speaking scientists. So these are some of the notable names are Planck, Heisenberg, Schrödinger, Einstein, Born. So really, and it was kind of natural because quantum mechanics very much started about where people were trying to understand atoms and elements and transformations of those, and they already were kick-ass in chemistry. So they're kind of a natural way for them to take over this field. And so by 1920, Germany's top, in both physics and chemistry, right? And so it's very natural that like all of those Hungarians, well, besides the fact that, of course, the Austro-Hungarian Empire was sort of culturally close to Germany, Hungary was culturally close to Germany, it was natural for them to go to Germany to study more and become and be at the cutting edge of the science of their day. So for example, our first hero, Leo Szilard, he goes to Berlin, which was a very happening city in the 20s. There he meets Albert Einstein and he impresses Albert Einstein. And in fact, together they work on new ideas for, any guesses? Refrigerators. Maybe you didn't think this was coming. So they were actually both touched by articles that they read in the newspaper. So old refrigerators had these essentially chemicals, right? The refrigerant or that would get pumped in the back of the refrigerator, which we have now, but they weren't as good. They were kind of toxic. And once in a while, there would be like a leak in the seal and the toxic fumes would get out and people would be asphyxiated. And they were very bothered by this. And so they decided to work on a new technology for refrigerators that used sort of electromagnetics and didn't have any valves or moving parts. And so there wouldn't be any danger of leakage. And they patented this thing, right? Because, you know, for those of you who know anything about Einstein, Einstein spent a lot of his sort of youth being a patent clerk in Bern. And so he was really into patenting. And so they actually had like a whole bunch of patents on these refrigerators. And they even made a few, but they had their own kind of electromagnetic pump. And that pump was so freaking loud that it, you know, they never actually wound up building those refrigerators commercially, but, you know, it made it pretty far, like, you know. And so, okay, so he finished with his like passion for refrigerators, and he was kind of a passionate man. He was smart. He was trying to figure out what should he do with his life. And he actually started getting interested in nuclear physics. And the reason he got interested in nuclear physics is because he's excited about space travel. What? Space travel? How does that link to nuclear physics? Okay, so let me explain. So you basically kind of have to ask yourself, where does the energy come from that we use in everyday life? You know, the thing is that mostly it's not that it comes from a source that's sort of new to us. I mean, we used to, as cave people, burn shit. You know, that's one source of energy, just burn stuff. I mean, we built windmills, we harnessed the energy of the wind. And of course, you know, we built water wheels, harnessed the energy of water. And okay, modern life, it's not like this has changed all that much. We still burn shit. That's actually mostly where we get our energy. So we still use wind, okay, a bit more clever in the design, looks a bit sexier, but still the same principle. And we still use dams and, you know, use those to generate electric power, you know. So we have all these sources for energy, but where is the energy ultimately coming from? It's just coming from the sun, right? All of this energy, like the stuff that we burn is really ancient plants. The wind is really the energy is coming from the weather, which is powered by the sun. Water, again, is flowing because, you know, clouds make rain, you know the story. It's a cycle of life, you know, it's all run by the sun. So if you want to go deep into space, all this stuff is not available to you, right? So he realized this, and he thought, hey, you know, how are we going to ever sort of explore the universe, or, you know, or just leave the solar system if we're not going to come up with a different way to extract energy out of something? So yeah, in space, you can't use any of these sources. But there was this very, very vague hope that he had, which is that maybe you can use nuclear energy. So any questions before I tell you a little more about this, by the way? I should stop.
Well, yes, actually. Why can't you use the energy from the sun in space?
Well, eventually you could use solar panels. That might help, but eventually, you know, like, so imagine you're between stars, or, you know, the stars, or even you're out in the far reaches of the solar system, very far away, where the sun is just like a very small source, right?
Yep.
Yeah, so it's definitely useful if we're, you know, if you're going to fly to Mars, but not so useful once you get further out. Yeah.
Almost to fly to Mars.
All right. So what's the idea here? Why was he hoping that something having to do with nuclear energy? Well, you know, as I said, you know, the atom has this sort of electron cloud. So there's this sort of electric, if you like, charged entity, which is sort of the quantum cloud of the electron, which is really what we think of as setting the size of the atom. But inside the atom, totally not drawn to scale, is the nucleus, which is much, 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 much smaller than what is drawn here. And essentially, when people discovered radioactivity, you know, which is the nucleus emitting various either chunks of itself or very high energy electromagnetic radiation or electrons, these kinds of transitions of the nucleus seem to be associated with very, very large quantities of energy. So, you know, this is something that, in fact, Marie Curie noticed, probably one of the first ones. She's just realized that the amount of energy that's coming out during radiative decay is very large. And in fact, she kind of correctly guessed that this means that there must be some kind of new force. I mean, at the time, they only knew about electromagnetic force. And indeed, it's the nuclear force that various nuclear forces that lead to this energy. And so he was optimistic kind of vaguely because, okay, this is a source of energy, and he knew that this is not coming from the sun. It's something that's sort of sitting inside of the nucleus, but he had no idea how to build some process or how to extract that energy. But he wanted to try. So he was very motivated to do that. And so he goes to Berlin. Well, he was in Berlin at the time, and he decides to work with Lisa Meitner, who's our second character. Lisa Meitner is born in Vienna, moved to Berlin. She's one of the best nuclear physicists in the world at the time, already very much an established figure. And she's the head of the physics department at an institute near Berlin. He starts discussing with her as kind of being like for her to be his mentor and kind of develop his knowledge of nuclear physics. And another reason that he's very excited to work with her is that not only she's the top one of the top nuclear physicists in the world, but she has a long-standing collaboration with an amazing chemist, Otto Hahn. So this is them together. And they have a kind of interesting relationship, because in a way, she was a very proper Viennese lady. And it's not like they went out and partied or like would even go drinking outside of work with each other. But their kind of interactions during the work time were actually very close in a certain sense. Like they would sing to each other. She would hum classical music to him. In fact, even the fact that their scientific relationships existed at all was rather radical, because when Otto first approached her to try to collaborate, because he was a chemist, but he knew nothing about physics, and he knew that she knew a bunch about physics because she, for example, she wrote lecture notes after seeing Einstein give talks. She was obviously a woman, and this was a very radical thing to do. So their first lab, they couldn't even build the lab within the normal part of the building because a woman was not allowed in the physics building. So they built it in the basement. So she was allowed to work with him only in the basement for a while, and she was not allowed to be seen above ground, literally. But this collaboration of theirs was very strong, and they had very strong personal ties. Of course, eventually she became very famous, and she could be maybe the first woman professor in Germany. I wouldn't be surprised. I mean, it was a very early time. She became kind of well known and the head of the physics department.
So how did she become the head of the physics department if women were not allowed above ground in that building?
Eventually. I mean, not right away, or eventually. But when they first started working, it was still a very radical notion, right? I mean, okay, of course, Curie was very famous, but again, that was France. Who knows what? Like, the Germans, different culture. It was just these kinds of changes only began happening. So it was fairly radical for its time. Szilard very excited to work with her. Also kind of maybe not a main character, but kind of a character in a supporting role is her nephew, Otto Frisch, who's also a physicist, talented guy. He becomes a professor in Hamburg, play a role later on. Okay, so if we stop right now and we just kind of look at the picture, here I've included our main characters, Lisa Meitner and Leo Szilard. They're in Berlin. Also kind of, I put Einstein there, still in Berlin. And then I've sprinkled some of the other Martians. They're all in Germany. And here's our supporting character, Otto Frisch. So, Germany was clearly the top in physics and chemistry in the world at the time. And all of these talented people, they were all essentially learning physics and being mentored by other more senior German scientists and pushing German science forward. Okay, but you know what happens next, of course, which is that Hitler comes to power, right? And Szilard's dream of becoming a nuclear physicist is right away destroyed. He gets the heck out. In fact, he barely makes it. He takes a train, he goes to Vienna. He was always kind of one of the advantages of Szilard is he was always kind of a bachelor type guy. You know, he would live in hotels. His belongings were always in suitcases, or he would couch surf. I mean, he never, you know, he didn't like put roots. So in a sense, it was fairly easy for him to take off, even though he's very disappointed because he wanted to work with Meitner. You know, he took a train to Vienna, and the train was basically empty when he took it. But 2 days later, it was full of Jews trying to get out of Germany. And at that time, it was already too late. You know, soldiers stopped them at the border and sent them all back. So he barely made it out. But this sense of his that, you know, shit's about to hit the fan was something that the other Martians from Hungary also had. And indeed, like, you know, they even left even earlier. You know, so they were kind of canaries. You know, like they saw this before. They had the experience of having the communist revolution, then having the fascist come into power. You know, they had no difficulty believing that bourgeois life could collapse instantly. And so they all got out, actually, quite amazingly. They got out pretty early. But what happened next, of course, is the mass firing of German Jews or other unwantables in early April. So about 30% of German professors at top universities lose their job. Imagine like just the intellectual loss for Germany at the time. By the way, I guess one thing I should say is that, you know, as we're thinking about this is, you know, the question of like, how anti-Semitism actually affected Germany's prowess in technology and war effort, right? That's kind of one of the obvious points here. So Meitner, you know, for a while, because she was okay because she's an Austrian citizen, and you know, she's not affected by the laws against German Jews, even though it turns out that she is in fact a Jew. So she was very much. She was part of the Viennese bourgeoisie. She never felt herself Jewish. I think her family even converted to Christianity, but of course that doesn't matter. None of that really matters. So she never was like an active Jewish person, but it's just, you know, but that was just the case. So she could no longer teach in the university in Berlin, but she could still do her research. And she was very embarrassed about this, right? Because she did her best to essentially, you never felt part of the Jewish community. She kind of hid it. She thought of herself as a proper Viennese woman. And she tells Hahn, you know, I'm really Jewish and I'm apt to be an embarrassment to you. So he, you know, their partnership is kind of course he doesn't care, but she herself, you know, this is the way that she feels. Wait a second, something weird happened. Okay, yeah, that's fine. Okay, good. Good. Okay, so Leo Szilard is very conscious, though. He's you know, he realizes that you know, all these scientists. I mean, he could see it ahead of time. In fact, that all these scientists are going to lose their jobs. And he starts trying to figure out how to get them work. And he winds up going to England. He has some connections. He tries to figure out how to get a lot of them hired. And then he starts sort of putting the word out there. And one of the people who was sort of very, even on his own initiative, very responsive to this change that occurred was Niels Bohr. So Niels Bohr is our next kind of character. He's a famous scientist from Denmark. essentially Niels Bohr, you can think of him as being the father of atomic theory. So, there's the periodic table that we see here. It was actually Niels Bohr who first figured out that the position of elements in this periodic table follows these numbers. And these numbers are in fact the number of electrons that the particular atom has. So electrons are a negative charge, and the atom is neutral because there's a balance between the number of electrons in the atom and the number of protons in the nucleus of the atom. So effectively, he realizes that this placement of the chemical properties of the elements follow from the properties of the electrons, and the number of electrons is set by this atomic number. He became very famous, not just because he understood the structure of the atomic theory, but also because he was able to, remember we said that one of the main first achievements of atomic theory is to try to understand, for example, the color of light emitted by hydrogen as it changes its shape from, let's say, the sphere to the dumbbell. And he created a model which technically is not true, to try to explain the frequencies of light. And he wrote down a formula using logic, which was actually clever and sound, except that it turned out later, once people understood more what was going on, that his logic didn't actually apply to the data. It didn't actually apply, for example, to specifically the transitions between the sphere and the dumbbell. Yet he got super freaking lucky in that the formula he wrote down somehow didn't care. And so by a complete accident of nature, he managed to predict those frequencies exactly right, even though the actual reason for it is not at all what he was thinking. But he got famous anyway. At this point, he's sort of a, very well known. I mean, he was also like an excellent bullshitter. And he was very, often people would be, when they were exposed to him, they would both be astounded and at awe and confused and in some sense hypnotized. And he sometimes would say things that were completely incomprehensible. And very often people would come out thinking he's a genius, but not being sure exactly what he was saying. And he himself had this sort of style of talking where he would just sort of linguistically explore possibilities as he was discussing. So, on the other hand, that was pretty much kind of what quantum mechanics was like. Quantum mechanics really had this feature of being kind of confusing and disorienting and somewhat, mesmerizing. And so perhaps it was very fitting that sort of the spiritual leader of quantum mechanics was this character, Niels Bohr. So at this point, he was essentially a towering figure. In fact, he was a rather large person. He was tall and had a very big head, which almost cost him his life later on in the war, but that's another story. So, but in any case, he's really a big authority figure. And one of the things that he did was he organized all sorts of conferences to save all the scientists who were now out of work. So he basically tried to position them and find them jobs. So, and one of the people that he actually found a job was Meitner's nephew, Frisch. Remember that guy? So he hires him in Copenhagen, which is where he works. So he comes up to him one day. He goes to Hamburg. Frisch is very worried that he's going to lose his job, and he kind of grabs him by his little button on his waistcoat and says, "We need people like you in Copenhagen." And Frisch is obviously starstruck because here is this giant of physics that's just offered him a job by grabbing his clothing. And so he writes a letter to his mom that says, "The good Lord himself has taken me by my waistcoat button and smiled at me." So he was, ecstatic that he would not be abandoned. And so he moves to Copenhagen. All right, so now we're gonna take a little change, since I originally actually gave this sort of presentation to a bunch of kids, but I'm sure there are Harry Potter fans in the audience. So you might know that the original British title of the first Harry Potter book is actually Harry Potter and the Philosopher's Stone. Anybody remember or know what the Philosopher's Stone was or was supposed to do?
Just speak.
The Philosopher's Stone is a stone that makes people immortal if you drink it.
That's right. So the Philosopher's Stone, one of its powers was, that it grants you immortality. Anything else?
It gives immortality to the person who owns it.
It gives immortality to the person who owns it. So the Philosopher's Stone was, obviously this object invented by dudes. And as we know, like, what do dudes want? They want to live forever and they want to have tons of dough. Okay, so essentially it was a magical object with mystical powers, and the study of an attempt to find this magical object was called alchemy. And it was indeed supposed to give one eternal life. It had this mystical symbol, and it also is supposed to give you power over the elements. And in particular, what it allows you to do, so here's some painting of like, someone attempting to create the Philosopher's Stone, is that it allows you to turn metals into each other. And in particular, of course, what you really want if you're a greedy dude, and is that you want to be able to turn all metals into gold. So the philosophers, the people who practice alchemy, they were really excited about this ability to manipulate metals. Okay, so that's something that is, of course, a fairy tale, but there is something in life which is kind of close to that, and that was discovered, or its power was discovered by our last character, who's Enrico Fermi. Enrico Fermi is an Italian physicist. Like everyone else, he was educated in Germany because, as we said, Germany has the best everything. What he discovers is not quite a philosopher's stone, but you could call it a tiny little mini pebble, which is the neutron. So what he found effectively is that if you take a radioactive source of neutrons, let's say radon gas, and then you expose elements to the neutrons, then what happens is that elements become radioactive and then they start changing into other elements, right? So you really can realize this dream of taking one element and changing it into another. And, for example, you could take a neutron and you could hit a silicon with neutrons. So it's like silicon's like this shiny metal. And then what happens is that the neutron is absorbed by the silicon and emits some radiation and emits an electron, and then it transmutes into phosphorus, which is something which looks completely different. So here you've taken silicon and you've turned it into something completely different, which is phosphorus. And so he discovered this, of course, like many discoveries in science, by accident. So, to get the neutron to be captured by the silicon, he has to be moving slow enough. Otherwise, it just shoots him like right through it, and that is not actually absorbed by the silicon. So he didn't think about that. No one thought about it because they didn't really understand the neutron was still a very new object. It was only discovered like in 1932. And so people didn't quite understand its properties yet. So, he couldn't get the reaction rates to transmute to be very good until one day, by accident, he put a piece of wax between the neutron source and the whatever material he wanted to transmute. And wax has a lot of hydrogen, and when the neutrons hit the hydrogen, they slow down, and so they're now slow enough to be absorbed. And so that was all the rage. So suddenly, like, he was able to get all these elements to change into each other, right? So here's his team. This is Fermi's team. Here they are sitting on the beach somewhere. They were working in Pisa at the time, and they were like these crazy boys in a way. They were just kind of very childish. They would, they had a corridor. So on one room, they basically irradiated the sample. So they would put the silicon there next to the radon gas, and then it would get excited. And before it fell apart, they wanted to record its radioactive properties. So they would need to run down the hall to another room where there was no radiation so that they can measure the properties of this radioactive substance before it transmuted. And so they would constantly hold races, running down the corridor with like vials of radioactive material, and sometimes colliding into people. Well, those were fun times, I guess, back in the day. But what they found using this, clever discovery of slowing down the neutrons is that you only change elements that are kind of neighbors in the periodic table. So for example, silicon we saw transmutes itself into phosphorus, and they're kind of neighbors. So you could get silicon to change into phosphorus, or aluminum or the silicon to transmute to each other. So they studied basically everything on the periodic table, and every time they found that like the changes that they could create, they're not radical changes, but they're kind of local on the periodic table. So any questions about this little bit of science? All right, cool. All right, and meanwhile, Szilard, still kind of in the back of his mind, always thinking about nuclear energy and how to really extract it. He's kind of walking around London, a little bit despondent. He's about to cross the street when suddenly this vision appears in his head. And he imagines something which we now call a chain reaction, where could it be that if a neutron hits some kind of nucleus, if more than one neutron comes out on the other side, then the products can then hit further nuclei, which can then hit further nuclei, and this goes like a reaction, kind of like a virus, right? We talk about the replication rate, right? So the idea being that, if a person can infect more than one person, then there's a chain reaction. So this is in fact something that he thinks about when he thinks of, because he was inspired by chemistry and biology and other things. And so he has this vision. But it is just kind of an hallucination. I mean, he's excited because that for the first time there is a mechanism, for how to create a chain reaction, and this really could be a source for energy. But he doesn't know who any of these characters are. He has no idea like what to shoot at what and how this would actually work. It's just this vague notion, but being a practical fellow, he actually goes and patents it, with the Brits, but he does it kind of secretively because he realizes that, that this could have a military application or something like this. So he's careful about his patent. Then 1938 rolls around and things become worse. For one thing, the Nazis enter Austria, and they're met by cheering crowds in Vienna here. And so now Lisa Meitner, who was an Austrian citizen, is in danger, right? Because before she was being protected by the fact that she was Austrian, but now she is, a Jew under the jurisdiction of the Nazis. And so everyone gets worried about her. In particular, she is kind of the quintessential forgetful professor. So she's very not practical. She lives in like the world of physics, and that's part of the reason also that when the first crisis happened, when there was the massive expulsion of scientists in Germany, she still lays low. She does not leave the institution. Of course, it's also understandable because she obviously struggled really hard just to get that position and to be able to be kind of a person of authority, right, in this department. She doesn't want to abandon it, but also because, that's her entire life. Her entire life is science. And so the other scientists, they worry about her because she's so impractical. And one of her collaborators, she writes him a letter, Dirk Koster, he's a Danish physicist, You know, he begins to worry about her. He tells Bohr. He decides to go to Copenhagen, to go to Berlin to escort her to Copenhagen, to get her out of Germany. Okay, and so Koster and Hahn, like they gather at her apartment. They help her pack her stuff and get her ready for the journey, put her stuff away, and you know, as a sort of if you like, a token of the strong bond that Han and she has, you know, he gives her a diamond ring that has been sort of in his family for generations, and he gives it to her as just, you know, in case of an emergency. You know, this is what, you know, if she needs some kind of money. So he gives her the ring. They pack her stuff, and then they Der Koster takes her. They go take a train. So they could take a train from Berlin to Copenhagen, right? So at the border, Nazi soldiers board the train, right? And so you've seen this scene before. The Nazi soldiers board the train. What do they say? Papieren, Papieren, right? Except that, of course, again, Meitner is a nerd, and her passport has long ago expired. So they take her expired passport and disappear. You know, and she's sitting there with Koster, like afraid for her life. And they're gone, and they're gone, and they're gone. 10 minutes later, they return, and by some miracle, they let her go. So some scene which is completely out of a movie that, you know, this is one of the big mistakes. I guess this is one mistake that Nazis have made with this, by letting her go. But they did, by some miracle, even though her papers were expired. Okay, characteristically un-German of them. Okay, so she winds up in Copenhagen, and you know, Bohr arranges a job for her in Stockholm in Sweden. And so she's out of Germany. Also in 1938, Mussolini finally decides to support Hitler. And so in July, it is declared the Jews do not belong to the Italian race. It so happens that Fermi, the guy who used our little mini pebble, is married to Laura, who's a Jewish woman. And so the Fermis decide that they have to leave Italy as soon as possible. So Fermi starts contacting people around the world. He finds himself a job at Columbia. And he needs to make his way to Columbia, except that, of course, this is a situation of war. And so, you know, the Italian law forbids, you know, when, you know, you can't just take money out of the country when your country is about to go to war. However, luckily, Fermi wins the Nobel Prize in Physics that year. It wasn't a complete coincidence. He was kind of told by the powers that be that should he need the Nobel Prize in Physics that year, he could get it. And he, of course, says, yes, please. So the Fermis go to Stockholm. They collect the money from the Nobel Prize, and then they go to America, where they now have money to, you know, find a house and so on. All right, so I think we've gotten to the end. Yeah, this is a good place for a break. So, you know, the stage is now set. You know, I'm showing you the map of all the different characters. You know, maybe before we break, let me just make break. Yeah, I know. Just a few comments. One, of course, is the obvious point that all this talent that Germany had is completely scattered across the world now, right? And in particular, here are, you know, some of the characters. There's Fermi and Szilard. They're actually now in New York. Some of the other Martians are also in the US. And of course, the irony is that just before, all of these people were happily pursuing careers either in Germany or in Italy, right? So they were kind of happily working for Axis powers. And just to also, you might say, kind of make it very clear, besides Einstein here, who really was a pacifist and kind of did not really believe in contributing to any war effort, many of the other scientists didn't have such qualms, right? So, Otto Hahn, for example, Meitner's partner, he created some of the vicious chemical weapons back in World War I. Meitner herself, she didn't create weapons, but she, for example, used her knowledge of radiology to help treat soldiers. So many of these people, and of course, these other people here, they were about to join the army, the Austrian-Hungarian army. So it wasn't that you could imagine a different history by which all these people would actually participate in the war effort on the German or perhaps Italian side. So that's one comment. The other comment, which to me is still kind of, well, since I work in academia, it's kind of amazing that they all have jobs from my perspective. It's kind of amazing that whatever the system was at the time, there was this sudden diaspora of scientists. And of course, I'm telling you about a few of the characters, but you have to imagine there are many more. And that they were all able to find jobs in all these different countries on fairly short notice. And, one thing to say here is that this is all happening before sort of physics is famous, as a contributor to, let's say, like, I don't know, the industrial complex, right? I mean, in the sense that the stuff that these people are all working on is very, very obscure at this point. It's not something that is obviously linked to technology. It's various properties of atoms and so on, or nuclei. None of this has been turned into sort of maybe radioactivity is used in medicine, but basically that's it. So, it's not that there is a very strong track record of the specific science that they're working on. Moreover, of course, there are only just a few of them in the whole world. So like, people understanding nuclear physics at this point were, I don't know, maybe there's 100 or 200 people in the whole world. So it's a very small community, and it's kind of, you would think, it's not at all obvious why it was possible for them to find jobs.
So I actually have a question, but yeah, this was clearly before tenure was such a complicated process. But at what point of time does someone realize the possible applications of this and like the whole military race? And
yeah, so I'm about to tell you, right? That's kind of the point. But before, it wasn't very clear. Again, right? Like, at least let me list again the technologies that quantum mechanics really revolutionized, right? Which is the computer devices, LEDs, lasers. All these things are things that are invented much, much later. We're talking, 50s, 60s, and so on, right? So those enormous industries, and of course, things that having to do with nuclear technology, that has not come to be yet. So these people are working on fairly obscure problems, yet they were somehow able to find jobs.
Why was that guy so interested in traveling to like other galaxies?
He's a dude. I don't know. Just like imagining various things. He had to figure out what problems to work on. It was kind of just general motivation. It's not too different than the way that scientists work nowadays. For example, people try to build quantum computers, and they bullshit, and they write various proposals to the government how they're going to build quantum computers with this, and that. But to some extent, they don't really know. Very often, they develop various technologies that have to do with very intricate properties of quantum materials. They don't really know how to assemble those properties and make them into a quantum computer. So, there is a tradition of scientists kind of having very lofty goals but in the meantime, trying to meet various technological or scientific needs, along the way.
Do you think that there is some kind of think tank that were able to identify all of the Martians and help them find jobs in the US?
No.
Is this like one of the
not yet
conspiracy theory?
Not yet. It was just kind of, Zillard was a smooth operator, for example. He found some guy who had a loss in the family associated with cancer, and that guy wanted to invest in various treatments associated with radioactivity, like which weren't ready yet. So Szilard found himself a gig that way first. Fermi had a Nobel Prize. So, okay, at that time, Fermi was very famous. He had a Nobel Prize. Einstein, of course, was the only person I think that who globally was fairly famous is Einstein. So when Princeton or like the Institute for Advanced Study hired Einstein, that was kind of a no-brainer. But, these other people, Neumann was hired because, they thought that they should have Neumann was also very, very, he was a wunderkind. He was able to solve every single problem, essentially. Other people that people considered geniuses thought that Neumann was the biggest genius ever. Who could do, so I think he was a unique case, but look, I've been on committees. That's why I don't believe in conspiracy theories, where it's obvious who should be hired, but explaining that to the other people is like an endless political battle, right? So I can imagine what went on, when they had to hire like Teller or Wigner, or how Bohr was able to get Meitner like a position in Stockholm. I don't know. Well, Bohr's famous, but still, famous people are not always powerful enough, depending on the sociology. They're not always powerful enough to, go around, let's say, a university administrator. That's kind of been my experience. It's not at all obvious, right? So it's something about the way that the networks were set up at the time where this was still possible.
But also academia was a little different back then.
Yeah, in fact, that's right. But even more shockingly different, right? Because there wasn't this idea that there should be massive investment in science, for instance. So it was harder on some level. Scientists were closer to being in the humanities, especially in some obscure physics thing where the application wasn't clear.
Yeah, but I feel like educated people were kind of treated differently, even,
Okay. That's the right. Exactly. That's right. So culture was different. That's right. Yeah. All right. Want to take a break? Let's chill for a bit because I think I've introduced all the characters and the next is just a bunch of plot.
All right. So should we say 5 minutes?
Yeah.
Okay.
Yeah, I guess maybe you should stop recording.
Yeah. Yep.
All right, good. So the plot begins. So that's the setting, and things start more or less pretty innocently. Essentially, it starts when Hahn writes Meitner a letter. So remember, Hahn is in Berlin doing his experiments. Meitner is now in Stockholm, in Sweden. In fact, it's Christmas. It's around Christmas, and she's on a family vacation in Kungälv, Sweden. I don't know if any of you have visited that place. It's supposedly very pretty, and it's winter, of course. And interestingly, her nephew, Frisch, also joins because he's her nephew. And so, what Hahn is telling her is he's finding the craziest thing, right? He's finding that when neutrons hit uranium, right? So, they tested all these different elements, right? The Fermi and his collabs. And now essentially uranium was always very confusing. And finally, Hahn decides to really try to figure out what the heck is going on with uranium. And he finds that when neutrons hit uranium, they make barium. Okay, this might sound kind of, really? Okay.
What's barium?
What's barium? This is barium. Barium is so what's crazy about it is that remember that the changes, the transmutations that we were discussing before, they always happen very close on the periodic table. But uranium is number 92 over here, and barium is number 56. So they're really not close at all, right? They're essentially, barium is half the size of, half by mass of uranium, very roughly. And so that should not happen. It's very confusing. How the heck is this possible? And if it wasn't for the fact that Meitner trusted Hahn, she would have probably, someone else would have just said, oh, it's probably not barium, but some other element which is close to uranium, but maybe has some of the chemical properties of barium, right? Because he's a chemist. He's trying to figure out what are the chemical properties. But of course, Han is one of the most anal people in the world. He's super talented. He does incredibly difficult things to verify that this is really barium. And so when he's telling her that it's barium, she trusts him that it's actually barium. So this is a shock. She doesn't, he's essentially, he wants to write a paper, but he thinks that his results are coming out complete crap. So he's asking her, can you come up with any physics explanation for how this is possible? So she's very confused. And her and Frisch, they decide to go for a walk. So it's the morning, he comes downstairs, they read the letter together. Frisch is into cross-country skiing, so he puts his skis on. She doesn't ski, but she's a very quick walker. She says, don't worry, I'll keep up with you. So she's walking briskly, following him, and they walk and talk, and they try to understand, is this at all feasible? When suddenly she realizes what's going on. And what's going on is that uranium is this really, really big nucleus. So the blues are the neutrons and the reds are the protons. And from the perspective of a proton, it has many lovers and haters. So what do I mean by this? Well, there's this strong force for each proton sees neighbors, and its local neighbors are attracting it. So the nuclear force is local. It only works locally, and it's always attractive. But each proton is getting a lot of hate from other protons because they're both positively charged and they repel. So a proton here feels love basically from neighboring protons, but hate from some proton on the very other side of the nucleus. So just like in social networks where, your friends, they'll comment and love you, but someone you don't know is the one who you get the hate from, that's what is experienced by protons in uranium. So it's this kind of delicate balance where, it's getting pushed apart and also being held together locally. And at some point, something's got to give. So she realizes that the uranium nucleus must be very jiggly and unstable because it's balancing the local love with the kind of hate that it's getting from protons somewhere far away. And so she realizes that it's entirely possible that a tiny little neutron hitting the uranium can actually break it into two pieces because it's so jiggly. And when she thinks about this, the fact that it's able to do this and the fact that it breaks, say, into barium must release a lot of energy. And at first she's confused because she's like, where does this energy come from? But then she remembers Einstein's lecture. And she realizes that it's E equals mc squared. She realizes that the mass of the products of these reactions don't actually add up to be the mass of the original ingredients, that is the uranium and the neutron. There's what's called a mass deficit. And that mass deficit is basically converted straight into energy. So this formula, which we take to be iconic, itself was kind of obscure in the sense that when Einstein wrote this down, he's like, okay, that's true. What does this formula say? It essentially says, remember, we talked about the fact that energy is a universal currency of nature, right? You can transmute energy from one form to another. And what this formula says is that mass, it contains energy. So the very being of an object, so this cup contains energy, this glass, just by being. However, it's not obvious from the fact that it contains this energy that you know of a mechanism of how to extract it. So up until this moment, yes, in some kind of obscure situations, this formula was useful, but it didn't have the bite. It wasn't clear that, oh, wait a minute, we could actually turn some of the mass of this nucleus into energy. And so that's what she realized. And when she realized it, because she remembered all the masses to many decimal points of all these different ingredients, she was able to calculate, kind of estimate how much energy comes out. And, it all made sense given various models that they had. So obviously this is crazy. And her and Frisch immediately sit down to write a paper about this. Frisch goes back to Copenhagen and he tells Bohr about it because Bohr is the big boss. And obviously Bohr gets super excited, right? Because for the first time, you can actually make energy come out of mass. And he takes a boat to America with another physicist named Leon Rosenfeld. Now, he promises Meitner and Frisch not to talk to anybody about it because they're about to put out a paper and he doesn't want them to get scooped, except that he's stuck on a boat with another physicist and he's a bullshitter. So he's obviously going to tell this physicist about this amazing discovery. And even though he promised that he wouldn't talk about it, he forgot to tell Leon that not talk about it either. So when Rosenfeld finally he goes to Princeton and he's like, guys, guess what's true? And he tells the physicists in Princeton that uranium can be split in half. Okay, and of course, calamity ensues. This goes more viral than, the mittens. So, like every single physicist can only think about this and they start talking to each other. It just goes completely crazy. Like there's an uproar and so on. And eventually, Wigner, who actually is a physicist at Princeton, tells Szilard about this. And this, of course, is what Szilard wanted all this time. It's the chain reaction. He realizes that this is a very drastic change in the structure of the nucleus. And it's very possible that when you perform such a change, that there will be other neutrons expelled and possibly more than one. Of course, he doesn't know whether it's more than one. So he goes and he very quickly constructs an experiment in Columbia. So he now, by this point, has some kind of position in Columbia. He constructs an experiment in Columbia to kind of estimate, measure the number of neutrons, and he finds that indeed it's looking like 2, roughly. I mean, he doesn't, so, again, since we've all been reading viral literature to death, he's just discovered that the R factor is bigger, there's a potential for the R factor to be bigger than 1. So a chain reaction can happen. It's not obvious whether he can make it practical yet, but he at least locally, when the uranium splits, he's measured it. And so obviously, this is a huge deal. And he goes immediately to Fermi, who has, who's got a position in Columbia, and tells him that this is what they need to work on. They should drop everything and start working on trying to understand whether a chain reaction is possible. He, of course, gets scared right away, and he tells them that, you can't publish this result. That, there's no way that the Germans should find out about this. And they have a huge argument, and Fermi is like, well, it's science, science should be available to everyone. And Szilard says, no, this is not how it works, because he's a Martian and he's seen how it works. So, they start talking amongst themselves, and they, the Hungarians, they're kind of in agreement that this is top priority, that they should all work on this. And they're not really naive about it either. They realize that this liberation of energy could mean right away that there's going to be a bomb. And even at the very beginning, they are thinking what would be the consequences to society. So they think, should atomic weapons be developed, no two nations would be able to live in peace with each other unless controlled by a common higher authority. And they really hope that this would ultimately abolish war, because they realized very quickly that war is just impossible. A real war between technologically advanced countries is no longer fully possible. So even at the very early stages, as they're frightened by what Germany would produce, they're also already thinking about non-proliferation. Then they talk some more, and then they start really freaking out about the fact that Germany is about to invade Belgium, because Belgium is mining uranium in the African Congo. In fact, even until now, I think one of the most sort of full of uranium treasure places in the world is located in the African Congo. So they don't know what to do about it. Obviously, they have to somehow communicate to Belgium to get that uranium away out of the Congo. And then Szilard and Wigner, both of whom know Albert Einstein, remembered that, Einstein is, of course, a kind of famous guy. He had, various soirees, and he went to various select social occasions. And on one of these social occasions, he met the Queen of Belgium. So they immediately decide that what they need to do is go to Einstein and have him write a letter to the Queen of Belgium. It's a little cockamamie, but this is kind of their way of thinking about how they're going to deal with this. So Wigner drives Szilard to Long Island to meet Einstein, who looks kind of like this probably at that time. You see he's sporting very nice, fashionable looking sandals. He's got like his little shorts there. He's sort of, vacationing on Long Island, taking little cruises. They arrive and they start telling him all these things. And he's very surprised. He's like, wow, how come I never thought of it? He's a little bit older now. He's not following all the latest trends. So he's shocked to find out any of this development. And he understands immediately what this means, even though he's a pacifist. So Einstein happens to know, because he knows many people, this guy named Alexander Sachs. And Alexander Sachs is a famous economist. He's also a Russian immigrant, by the way, works for Lehman Brothers. And during a certain point, he actually was working in the administration of Roosevelt. So when he talks to Sachs, Sachs is telling him, this is very weird. What are you doing trying to communicate with the Belgian Queen? No, this is like, you're missing the point. You really need to go directly to FDR and tell him about this possibility. So, okay, Szilard makes Sachs convinces Szilard that, they're barking up the wrong tree. They really should go talk to FDR. And so Einstein and Szilard sit down and write a letter to President Roosevelt. This is the famous letter, right? The science was basically explained to Einstein by Szilard. They together draft this letter. They explain the various worries that they have, both about radioactivity and about the possibility of a bomb. And for a while, this goes nowhere. And then finally in October, Sachs finally meets President Roosevelt, holding this letter. Of course, Sachs is a smooth operator, so he doesn't actually read the letter to President Roosevelt, right? What he does is he opens up with a story about Napoleon and Robert Fulton. Robert Fulton was one of the people credited with inventing the steamboat. And at some point, he wrote a letter to Napoleon saying, hey, I can build you a fleet which doesn't require sail or wind, and you could use that fleet to get to England. And Napoleon is like, what? No way, and rejects that. And so, Sachs takes this story and clearly goes with it and says, what I'm about to tell you is that kind of information. You can't ignore it. So, as a joke, Roosevelt pours them both some Napoleon brandy. Cheers. He listens to Sachs's story. So Sachs is not reading really Einstein's letter. He's just kind of paraphrasing and giving him the bottom line. And Roosevelt says, Alex, what you are after is to see that the Nazis don't blow us up. And Sachs says precisely, and Roosevelt declares, this requires action. Okay, that's the way the decisions were made back in those days. Okay, so a meeting is set up to figure out what to do. It's a meeting between, essentially the army representatives and the scientists. So the Martians go to Washington, Szilard and Wigner and Teller. They all go to Washington. Fermi does not go to Washington because he already tried to get money from the government to do research on this. And not only was he told no, but he overheard someone referring to him as a wop, which was a derogatory term for an Italian. And so he's still kind of pissed off and he doesn't really want to go to Washington. So he lets Teller be his representative. He says, this is what I think, tell him what I think. So the meeting starts, there's a representative from the army, there's a representative from the Navy, they talk and they talk. The meeting doesn't go very well. In fact, the army representative gets up and he goes on a long blah, 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 describing how really it's hard to incorporate weapons into war. Wars aren't really won by weapons, but the morale of the troops. And this just goes on and on and on. And at some point, Wigner, who's actually one of the more polite kind of, he just loses his cool. And he says, he gets up and he has a kind of very squeaky voice and he says, oh, I find this very interesting. I always thought that, technology and weapons win wars, but if it's not weapons but morale which wins wars, perhaps one should take a look at the budget of the army and maybe the budget could be cut. He says that like when you're in front of all these top brass, and the army rep just relents. He says, all right, you'll get your money. And so they managed to get a little bit of cash, like a very small amount, to start their experiment. And so Fermi and Szilard get some money and they start experimenting on uranium at Columbia. So what they need to do is they first think of this as the same as Fermi. They need to slow down the neutrons, and they basically calculate that most cheaply and efficiently, they need big blocks of graphite. So they're assembling this sort of construction made out of graphite and uranium, oxide, which is basically this yellow powder in cans, to try to understand what is going to be the reactivity and trying to see if they can get a chain reaction to go. Fermi's very proud of himself that he's being a real man and carrying all this heavy load, but graphite is pretty damn heavy. And so, they to make this sort of prototypical reactor, which is what it was, they needed a lot of space. So they went to the university president because they can't just do it in their lab. And so the university president knows that they're doing some kind of weird experiment there. And one day he goes to visit them and he sees these like black, like covered physicists carrying heavy crap around. And he's like, what are you doing? Are you nuts? We have a bunch of hardy boys to help you out. So he says, why don't you take the university football team? They're strong dudes. They can help you carry the graphite. And so the university football team of Columbia puts together the first prototypical nuclear reactor. Okay, какой вопрос? Well, this is like 3940.
Yeah, the question is in the chat box. If you click on
sorry, I don't see the chat, but because I'm on the screen.
What's
But
happening with Meitner and her and Fish? Like, what are they doing?
as all of this is going on.
Okay, I'll tell you. Meitner is still in Stockholm, right? And Frisch is in Copenhagen so far. That's all going to change, but so far that's what's going on. Okay, so this is all happening in 1939 or so. Meanwhile, on parallel tracks, Bohr also is starting to think about all of this, and he makes a very important realization, which is that it's a different isotope of uranium. So it's not the more common uranium-238, but rather uranium-235 that's actually the most reactive one. So the fission is really being caused, like the reaction, if you like, the nuclear reaction is being caused by uranium-235. But uranium-235 is only 1% of regular uranium ore. So, he's very pessimistic that in fact a bomb can be built, right? So he convinces many physicists, and the kind of consensus among the physicists is that maybe if you have a ton of uranium, you could build a chain reaction. That in itself is not clear. It depends on how you arrange the uranium, if you have some engineering prowess, but building an atomic bomb is essentially unlikely. Unless you can extract uranium-235 from the regular uranium ore. So if you ever heard the term enriched uranium, what that means is there's more 235 and less 238. Okay, but at this point, they have no idea how to do that, right? So they kind of don't think about it. Okay, perfect. Now we go to the question, where is Otto Frisch? Well, Otto Frisch got very freaked out because the Germans are moving, and it's very clear that soon they're going to be in Denmark. So, his spidey sense tells him he should just get off the mainland, right? So he gets himself a gig in England, and he's working in England. And he sits there and he thinks of various ways of extracting 235. And he comes up with various techniques, although a lot of them are fairly intense. But just for the hell of it, him and this other guy, Rudolf Peierls, who also escaped from Berlin, also another scientist who left with Berlin, Peierls developed a certain calculational scheme by which to estimate the whole reactivity. And they do something that is a little bit unusual that nobody else thought about, because the fashion was that you need to slow down the neutrons to make the reaction happen. But they actually do something else. They think, but what if you don't slow down the neutrons? Like, can you actually get a chain reaction to work if you had uranium-235 by itself with fast neutrons that you never slow down? And they calculate it, and they find out that you only need several pounds of uranium-235. Then not only is this going to work, but that you only need several pounds. At this point, they're the only people who know this. I mean, it's possible Heisenberg also knew it in Germany, but they're certainly the only people in sort of the.
So you actually, so there was actually a question, like, why were they mining for uranium before they knew of these application? Was there a different application before this?
So, actually, funny enough, uranium oxide was used as a dye. Going back to in ancient times, that was also true. Also, uranium is still a metal and it has certain properties and was used in various ordnance. So it's a bit obscure. It wasn't like it was a very important foundational. You don't treat it with as much respect as we treat it now, but
it was good for something.
It was good for something, yeah.
And what are Nazis doing?
Sorry?
What are the Nazis doing?
The Nazis the Heisenberg is very smart, so he understands a lot of these things, but they're doing, well, at this point, they're definitely doing much better than everybody. They understand a lot of the ideas. They're also trying to build a reactor. And Heisenberg is he understands the various things. It's really unclear exactly what Heisenberg wanted or knew or did. But, he's concentrating on thinking how to build a reactor, which is also kind of what the Americans are thinking about. So, in fact, they're not at all thinking about a fast nuclear reaction yet. They just somehow didn't think about it, just like many times it works in science, because they were like, well, I don't know how to extract U-235, so why think about it? But they're shocked by this, right? They calculate. I mean, another thing. Well, I guess I should explain one thing about the science. I mean, it's not enough to have the chain reaction. The chain reaction. So what happens is that you have this uranium-235, and now a lot of energy is coming up, and it heats up, and when things heat up, they expand and they blow out. So you have to make sure that the neutrons keep finding targets before the whole thing explodes. So if it explodes too quickly, the chain reaction stops. And so one of their realizations was that there's enough time for the neutrons to keep hitting stuff before the whole thing is going to blow out. So the amount of energy that is being released is enormous. So when they realize this, they realize that the temperatures are going to be higher than the sun. The pressures are going to be greater than the center of the earth. It's like nothing they've ever seen before. And they freak out immediately. And they're shocked that it's just this tiny amount. That's not at all what they expected, right? Because they all were thinking in terms of the experiments and the results before, and they were thinking tons of material. And so they don't know what to do about it. And of course, they ask themselves, should they tell anyone? But, they do anyway, because they think, hey, the world's on the line. If the Germans figure this out, then we're toast. So Frisch and Peierls, they share this with the other British physicists, and the British physicists talk to the British government, and so Britain actually responds faster. Well, okay, maybe it's also under actual pressure at this point, right? It's engaged in war at this point. It's 1940. And so, they begin to invest in atomic bomb research. And so at this point, both Britain and Germany are putting more money into the atomic bomb than the US. And it's only in the US that this program is this complete conspiracy, this tiny little secret that only the president and the government knows. Of course, the generals, like there's some military people who and technical people who know this, but only the president is the only part of government that knows about this. And in fact, the US program is almost canceled in 1941 because they didn't know how to separate uranium-235. They didn't demonstrate a chain reaction yet. I mean, they were playing around with it, but they couldn't get, they lost neutrons. They couldn't get the R coefficient to be above 1 in practice. And they realized very quickly that, any application of whatever it is that they're developing, a reactor or a bomb or whatever, will take years. And the people in the government and in the army, they're like, well, it's going to take years. I mean, why we're worried about things now? Who cares? We should worry about making more bombs and planes and getting ready for war. And they didn't quite know about this Frisch Imperial's work. That work, though it was transmitted through certain channels to the US government, it was secret and it never really made it to the right people. So they don't appreciate the fact that you could actually make a fast neutron bomb. And eventually, through a very complicated sequence of events, the calculation in the report really does reach the right people in the US. In particular, a certain very famous British scientist arrives, and he's shocked that none of them really understand this. And he walks around basically convincing both scientists, US scientists, and other and people, political figures, that they should just immediately start working on this. And at the end, he convinces enough people, and when people see this report, finally there's an impact. So at this point, President Roosevelt actually authorizes a significant amount of money so that they can actually build a larger reactor, still in secret, but at least a real experiment, right? To see if a reaction can happen. And so they argue about, there's different scientists involved, and they argue where to build it. And at the end, they build it in Chicago, near the University of Chicago, which is where Fermi now moves to. It's called Chicago Pile 1. Looks again something like this. Is mostly graphite, and then in between the graphite are uranium, I think balls this time. And these are the scientists who worked on this project. Here's Szilard, and here's Fermi. And of note here, just because the way that it captures the spirit of the times, is Leona Woods. So Leona Woods is Fermi's postdoc, basically. And she built a lot of the detectors to measure the radiation levels of this reaction. She goes on to become fairly famous. She has prestigious positions in various top universities and in companies. Also, it so happens, by some quirk of history, that her second husband is the guy who invents carbon dating. So what people rely on to understand how old fossils are. But at this moment, she's married to her first husband, and as they're working on this radioactive pile, she's pregnant. And so she's handling all these materials, and she only tells Fermi about it, and they decide to not tell anyone. And so that sort of gives you a sense of how committed and how extreme the situation was. They were really committed to this scientific project, and they were willing to put all into it. So she works on it, and then she goes on to work in Los Alamos and go around. So they keep rearranging it, trying to get the thing to go critical. And so finally, on this cold morning, in December 2nd, 1942, the first nuclear chain reaction was created. So they turn on the thing, they remove the rods that are so famous in Chernobyl. They also create the system of rods. They remove the rods. The radiation in the pile gets going up and up, like the Geiger counters start clicking until it's just a deafening roar of Geiger counters. And then they start noticing that the temperature of the pile is going up, and then they shut it down before things get out of control. So it's very clear that, that success has been achieved. So this is the first time in history that humans essentially unlock an energy source which is other than the sun. And maybe even more kind of grandly, okay, although maybe the biologists in the audience can correct me. I mean, most creatures in our evolutionary history on Earth have basically got their energy from the sun. Maybe they're thermal vents or something like deep under like volcanoes under the ocean. But for the most part of our biomass, we get our energy from the sun. So it's kind of amazing that whatever evolution has produced eventually was able to unlock a very obscure energy source. Because remember, they had to engineer this thing. It's not at all like the sun, right? Like, again, remember that getting energy out of the sun is basically us copying things that we've seen in nature, which is why the cavemen could do it. But understanding how to properly arrange this configuration of uranium to be, you had to know a lot. So this was the first time that, this kind of energy source is unlocked. And so the physicist who's in charge, they're kind of the bureaucratic physicist in charge of this Chicago pile, calls the director in Washington, D.C., and he tells him, "You'll be interested to know that the Italian navigator has just landed in the New World." The Italian navigator meaning Fermi. And the director asks him, "Is that so? Were the natives friendly?" And he says, "Everyone landed safe and happy." So, and this is basically the end of our origin story. So this successfully proves the physics is right. It creates a series of essentially a whole industry of various centers and factories to be able to extract uranium-235 and then also to make plutonium, which I didn't tell you about. Across the whole America, it at the end winds up costing $23 billion in today's money. It employs about 130,000 people towards the end of it. And of course, the result of this is the frightening weapon, the horrible weapon that we know of. And this picture is the first explosion of an atomic bomb, which was in a site called Trinity in New Mexico. So this is the end of the story.
Yay, thank you so much.
Okay, well, I don't see the chat because I have my
Well, I can read that too. So the first question was what happened to her baby because she was, pregnant and working on this radioactive
had 7
substance.
heads. There was no problem as far as I know.
And then Shortman is asking what challenges are Iranians and North Koreans facing currently in terms of obtaining nuclear weapons?
Well, they're not facing any challenge. Well, I mean, Iranians are more facing, but North Koreans have nuclear weapons, right? They're in fact, but in a certain way. Look, I mean, I'm geopolitically talking to my sort of nuclear physics friend. I mean, he's worried more about Pakistan, to be honest, because whereas North Korea has nuclear weapons, but it doesn't have kind of an industry that keeps trying to push nuclear weapons, further and further to become more and more deadly, right? So this was the first weapon. This is a weapon having to do with fission, right? The breaking apart of uranium or plutonium. But later on, in fact, Teller, that same one of our Martians, him and Oppenheimer essentially devise a different kind of weapon where they use this explosion to trigger the fusion of hydrogen into helium. So basically the same kind of reaction that happens in the sun. And that fusion instead of fission is in fact even more energetic, right? So nowadays the most lethal weapons are fusion weapons, right? And those are the weapons that are being constantly developed, for example, by Pakistan. More and more kind of advanced versions of that. And if you are very confident about the government in Pakistan and its ability to control all these weapons, maybe you're not worried. But I mean, I guess he's less confident. I mean, he thinks of that as more of a worry, and he works in nuclear non-proliferation than, for example, what's going on in Iran in practice.
Question. So clearly, like, the whole point of the talk is like what happened during the war, right? And all those guys are Jews. Like, do you think that,
Not everyone.
well, but like if it didn't coincide with the war, like we would have still had the just like, I mean, in a matter of a few years here or there, we would have still had the bomb, or like eventually, or
yeah, I mean, I would think so, because it's just human nature, right? I mean, you would have to have a country. Well, I mean, it took an industry, right? So in reality, building the bomb, was something that in some sense only like an economy like the US could do to begin with, right? Of course, once the method is perfected, maybe it's cheaper. But to getting to the right, figuring out how to both build it, deploy it. I mean, there were all sorts of things like later about how to ignite it. There are all sorts of technical challenges, also how to obtain the material. Most of the money was spent basically obtaining the material, the more kind of enriched kind of uranium. But yeah, I mean, I think that, the physics was there. I mean, it's impossible to think that people would just not, I mean.
Yeah.
Yeah, I mean, I guess like this would be a ridiculously hypothetical question, but would they have gotten the funding for their research if there was no war going on? And obviously, we don't really know.
Yeah, I mean, like, look, I mean, part of it is also, there was this sort of change, right? I mean, I must say that, the reason I emphasize this sort of fast neutron calculation by these two guys who are now in Britain is because the people working in the US were thinking that they were making kind of reactors. They weren't thinking like in their everyday sort of work, they weren't thinking about the bomb. They were actually thinking, okay, we're going to make a reactor. Maybe it'll be useful for a submarine. Maybe it'll be useful for something else. So I'm sure that work would continue. I mean, and once you have reactors, you can make plutonium, for example. So then that makes the bomb much more likely. In fact, the fact that they figured out that if they have reactors, they can make plutonium also helped ignite the actual more concrete bomb research. It was a combination of the British information plus the fact that they realized that they could make plutonium, which is, maybe another source instead of the uranium-235.
У меня-то такой басовый самый. Нормально, он греет, очень греет. Да, невозможно.
Huh? Oh, I thought.
Is someone trying to ask a question?
Yeah, I'm trying to understand.
We're just getting a lot of noise.
I have a question.
Sure.
With which point, in your opinion, did like serendipity of this stopped and like the outcome was inevitable in terms of approximate timeline? So I understand that eventually they would have come to this, but in terms of making it happen, by 1945, at which point it was a matter of months and not sort of an open problem. And depend on getting funding and depending key people.
No, I mean, once they, that's why I stopped where I stopped. Once they demonstrated, like they were the first to actually demonstrate, right? I mean, that's another thing that you have to, think about how shocking it was that they were able to proceed with this, right? They were doing some very obscure work. They had zero experimental evidence for this. This was like a completely theoretical thing, and they were all thinking about it, but think about this for a second from the perspective of an administrator. Administrators were constantly doubting that this makes sense. It's not that they came to them with like ready technology or a ready process even. They were saying there's a completely new process in nature that no one's heard of. There are only a few hundred people in the whole world that even understand what the hell's going on. So it wasn't like there was there were even intermediaries, right? Like very often you could talk to someone in the military who has some technical experience, and that technical experience has some overlap with, with some physics. And so you can explain to them like what you're doing. And whereas for them, it was like they were really at the cutting edge. They and all these ideas were completely theoretical. So they were constantly being told that this is not going to happen. Right? I mean, I gave you only one meeting, right? But they had a bunch of these meetings, and like the head, like that's why it almost stopped. It almost stopped. So I think it only became a real thing when they built that reactor. I mean, because
So
once
1942, that
yeah, once they built that reactor, they showed that the reaction is possible. That became so. That now like they have several tracks, right? One is to produce uranium-235 through various clever ways, right? But also not to just make plutonium. And in fact, one of the bombs they dropped was plutonium. The other one is made by uranium-235. By the way, I guess I should say, just as a kind of, remember our story started with Belgium. Well, that uranium, they did save that uranium. That uranium-235, which was these powders of yellow cake uranium, wound up on ships, and they were actually taken out of the Congo, and they made it to Staten Island, and there they sat for a long time. In fact, they almost lost them, but they did make it to Staten Island, and they needed that uranium to actually make the bomb that they dropped on Hiroshima. But they were using it for other things. They were using it, as a metal. Yeah, yeah. Why? Someone asked before. Uranium was. Uranium was useful as a metal. They used it to like build stuff before. It had uses.
So Ami, why do you think they actually made it first, given that they were behind?
Oh, why Americans made it first?
Yeah.
Well, because
this particular group, yeah.
Well, I mean, they had the brain power, and then they had the industry, right? I mean, at some point
there were all these other people scattered around who were working on it, and the British.
So there was another technical thing. So, for example, the Germans, the Brits were just like in war, right? So they didn't have a huge country, right? They were an island with being bombed in war. They weren't the ones that they wouldn't technically be able to do this, right? This is basically the government built an industry from scratch. And this was the first time that there was an enormous investment of government money in such a fairly complicated scientific project, right? So this was kind of unheard of, right? Like it's not the way people developed, weapons before, so they needed kind of, they needed luck. I mean, a part of the reason I'm telling you this is that you see that this was not a democratically made decision. And it's also not a decision that was made by even like a small group of politicians. It was basically a decision made by just a few people in government. That's what's amazing about it, right? The few people, it was a time when just a few people in government, in particular the president, who had the executive power, could build an entire industry employing 130,000 people in secret.
So you're trying to make an analogy there?
Yeah. I mean, it's rather shocked. Part of the reason I'm interested in this and is my question, like why we can't do things like this now.
Because we're just a bunch of consumers. We're just sitting around, waiting for the toilet paper.
Wait, but we just had a president who tried to do things all on his own without consulting anyone. So maybe it's good that that's not really happening anymore.
Right. But we're also as a society, like, I mean, okay, we'll see what happens, right? I mean, like the analogy here would be that, COVID is a deadly virus affecting, hundreds of thousands of people. Why isn't there a COVID center? Why isn't there the Manhattan Project of COVID? Why isn't there a government investment in a center containing the top, whatever, biologists, epidemiologists?
But there is. But there
Yeah.
is.
Is there? Where
And
is it?
There's a corollary question to that, because FDR also created the New Deal. And why don't we have a second New Deal now that would help get us out of this economic problem?
That's what I'm
I mean, I think,
You already created a lot of jobs before that. There was already a template during the Great Depression where hundreds of thousands of unemployed young men were like building trails or
Yeah,
like cabins.
I mean, I think the problem is that we got stuck with Trump
Even
during
jobs that
COVID and
were,
not
like,
FDR.
But also there is a lot of money going into research on COVID, a lot, and places like Harvard and Harvard Medical School and everywhere else.
But as you know, with science, and like people have to be in the same place. It's not the same. Like, okay, now it's kind of hard, of course, because COVID has this specific thing to it. But I don't know. But like in general, there should be like, it's harder when part of the way that they solved all these problems is they were together. Right? They were sitting, and this was their only research interest. Like they basically stopped their academic jobs. They went to a particular space where all of them sat together, and you had like the best.
Well, I mean, you don't need that now, right? You actually don't need to be in the same space physically now.
You don't to some extent, but like, I mean, I don't know. Is there an infrastructure for this? Like, are the people who are working on this? Is this their full-time job?
So I know that a lot of research kind of switched to that, and there is a lot of funding going into it. But
is there a coordinated effort to create a community who's in full-time job? Like every day they meet on Zoom to like figure out, like people of different disciplines. Like when they need, when the biologists need something, they talk to the epidemiologists. With the biologists, they talk to the mathematicians. Like that's what it was like. They were all in this like area, right? And they constantly, they would bounce off ideas. There was a lot of technical things for them to solve to be able to get to this, however horrible. But
I mean, maybe there's some really esoteric stuff that people are working on now that the media doesn't even know about, that eventually will just defeat all like respiratory viruses. I don't know. Maybe we won't even live to see that, but maybe as a result of all of this, it'll.
Sure. No, I agree with you that that in general, like with time, they didn't have to. The time was of the essence there, but kind of time's of the essence now as well.
Sure.
Right?
It is.
Yeah.
I mean, I think right now we're kind of grasping at straws in a way.
Like in some way, like what happened with the vaccine is a similar example, right? Like because the Chinese scientists and doctors decoded the DNA like within like a month or two and posted it online. And then this guy, who like the vaccine was ready before, the epidemic officially hit the U.S. Right? I mean, the science behind it, like they already knew because it was like something that was already discovered, right? And then this they looked at it because the U.S. government was like whoever is in charge of that, like they contacted the scientist who was like on vacation in Utah or whatever, skiing in January. And they looked at it by and then they had it, and then they were collaborating with Moderna, and so they sent it to Moderna, and that was all and then it took another 8 months to actually do the trials, but everything was done by February, they had the vaccine.
That's true, but to me that's kind of closer to the early phase where they built the reactor, but then afterwards they built an industry over, of course. So they built this industry that of different plants that are connected to each other. I mean, there was infrastructure, right?
No, but I mean, I guess that all goes to my point that, in the 1930s, America was already used to creating these.
Yeah, no, maybe you're right. Maybe that's
creating hundreds of thousands of jobs.
Right.
Yeah.
They were much luckier because they had FDR and we had Trump. I think that's really the answer.
The infrastructure to develop a nuclear bomb versus the infrastructure to vaccinate millions of people is a little bit of a different thing, right? You need one factory for a nuclear bomb, like
No. They had four. They have 4 or 5, and they, you know,
you know what I mean? But like this is kind of a
yeah.
different.
But we're also a little more advanced, right? We're not in the 40s,
but
right?
here,
So-
I mean, in this, but here it wasn't just that, because we've had some active, you know, misinformation and all sorts of like, you know, almost like sabotage of this.
Yeah,
effort
but
to-
I think
don't
I
know.
think it's actually more endemic than that, because I think what Ami's trying to say is that like the culture of this country has changed so much since the 40s that this kind of like centralized organization isn't even possible anymore. That like what FDR was able to do with the office of the president just has been eroded so much in the decades since World War II that we don't have that kind of government anymore that could handle this kind of like major undertaking.
Well, I mean,
we don't have like, I guess maybe in terms of healthcare infrastructure, but you know that was a problem.
No,
Yeah.
I don't think it's only healthcare. I mean, I think it is an illustrative example of like how the federal government in the US functions now compared to in the 40s.
I mean, for
Well, I think maybe that was the only time when the federal government actually did function like that.
Possibly.
And that's because, yeah, maybe that's because there was a depression in the World War.
Yeah.
The war gives the president very specific powers that they usually, I mean, they actually during the in the pandemic, he and Trump did a little bit invoke some of them, and Biden can, but they haven't actually, like mobilization of industry and all that stuff, telling different industry to like stop producing whatever shit to profit and mobilize, basically mobilize for the
war effort.
Effort, like that's something that they can. This is very unique for very like specific situations, specifically war.
Well, but they were able to pass New Deal, which gave a lot of people jobs without being called socialists. You know what I mean?
But I mean, about that, like the even now for pandemic, they could have done it, and they actually did indeed. Like even Trump did do some of that, but he just didn't do enough of that. Like just telling industry to reroute, basically to focus on what the like centralize again, like
Yeah, but getting to this idea of like rerouting. I mean, one of the main confrontations at some point between one of the bureaucrats and one of the other like scientists I didn't tell you about, who is like those of you who live in California know about the Lawrence Livermore labs. There's this guy named Ernst Lawrence. He built the first like collider, cyclotron. In fact, he was the main candidate to manage the whole Manhattan Project in Los Alamos, except that the general finally chose Oppenheimer over him. But at some point, like a government bureaucrat, I mean, they had a standoff, and Lawrence was saying, you have to commit to this right now. This is an important thing. And the government bureaucrat was like, yeah, well, are you going to abandon all your other projects and commit to it if you think it's that important? And like Lawrence was floored for a moment, but then he thought about it and he said, yes, if that's my job. And so he was, if it was a change of mind, right? Like it doesn't, it means that's my job. It means that it's not like if you're, for example, if you're an academic, you don't teach, you just do that. Like the government tells you that's your job.
Yeah, I mean, I can say for sure that even as somebody who works in a hospital, like my job is not now suddenly to fight COVID. Like I still have to do everything else in my job.
Exactly. And we all know, like, it's a totally different, if your entire, like, part of the reason is that when, again, this is difficult for COVID to get everyone in the same space, but even if a whole bunch of people, of various talents are told, we are sponsoring you, this is your job.
It's completely different.
Completely different.
No, but you see, like, again, the Manhattan Project was a small part of the mobilization in
Sure.
that occurred in general. Like people were like I think I read something like that 40% of like all the vegetables that Americans ate during the war came from like their own victory gardens. Like how much propaganda is required to even like make people start doing that? And then people change their lifestyles in all sorts of ways. Like there were all these like meatless Tuesdays and blackouts, even though America was like never actually bombed.
Yeah, but there was still a huge number, or a substantial number of men who was sent.
Well, yeah, that too. But somehow, I don't know. I get like.
I mean, we have all of those circumstances now.
Yeah,
like
we have circumstances that are worse than that.
Right.
Now.
So we could be acting that way. Like this country could be doing all of those things.
Well, if half the country is being convinced to, not believe these things, and then then you can't.
I think there's a lot of different socio-political reasons.
Yeah.
Cool.
I mean, I guess I guess we see that the regimes that have a tighter lid on propaganda have also a tighter lid on COVID. That is undeniable.
Yeah, but I mean, at the same time with COVID, look at that. Like, it's still like in Germany, it's still very hard. Israel.
Yeah, but that's not what I'm talking about. I'm talking about China.
Of course, there could be a selection bias in place where the regimes who have a tighter hold on propaganda can also manipulate public numbers and data. They don't have an active media that is like going to uncover.
I mean, I guess but you could say that like South Korea and Japan have, soft propaganda or
Thailand.
Right.
Yeah, I mean, you can
they're like different forces at work here, but when the society is so divided sort of against itself,
I would agree with that.
But certainly there must have been political division in the 40s too.
Not that much. I mean, certainly there were some German sympathizers, and I guess there was this infamous like Nazi rally in New York or something. And
okay,
there was like a big anti-communist
but all of those.
But that's another thing that is worth noting, that somehow that didn't play a role. Like so again, like the culture was very different. So when the general in charge of deciding how is the Manhattan Project going to be run, when that general made his decision and he interviewed Lawrence and he interviewed Oppenheimer, he chose Oppenheimer. Oppenheimer was a commie, right? At the time where like there wasn't really, amongst like the military brass, that was not like even before the McCarthy hearings or whatever. He also had, weird affair. I mean, like obviously putting a government lab, they researched the hell out of him. He had strange like affairs. He was, he learned Sanskrit and like read the Bhagavad Gita. He was kind of depressive. I mean, he was a very different person. He also didn't have some kind of resume. He didn't run a lab. He was a theorist, right? And despite all of that, like despite like what you would think would now be like irreconcilable cultural differences, this guy was talked to Oppenheimer, and he talked to the other guy, and he said, Lawrence, he's very smart, but Oppenheimer's a genius. And so I'm going to let Oppenheimer run the lab.
Yeah, that doesn't really happen these days.
I can't imagine that. And part of, it's just, it's like a cultural thing. It's in some ways, I mean, I guess it was the fact that they all went to same schools or, had similar education or whatever part, it was some sort of a boys club or whatnot on some level. So the decision was not made in public. That's another thing, right? Nobody was watching this general make this decision, right? It was a decision. It was just his call, right? So some difficult decisions weren't made democratically. They were just made by people in charge who were like, this is what needs to be done.
But if I can argue that they also rounded up all the Japanese citizens of the US and put them on camps. So it's a very questionable situation of letting one person make all the decisions.
Sure.
Well, I think
I'm not saying we should have totalitarianism.
I think that's largely because the Japanese physically attacked, U.S. territory. I guess they
right, but you can't round up American citizens.
I'm not making a justification for it. I'm just saying that, if the Germans attacked U.S. soil in some way, then maybe you would have had like German Americans being interned. I don't know. It's not totally
right.
clear.
I'm just giving an example of a negative,
sure,
effect of centralized power.
Yeah.
Right.
I mean, it's certainly not. I'm not exactly. I don't think we're saying that. The U.S. in the 40s is something that we should just totally emulate.
Yeah, we're not saying make America great again.
I don't think I don't think any country in the 40s should be emulated, because otherwise we would just like basically kill the shit out of each other.
Right. But it's more just the fact that certain decisions, that people need to trust certain decisions to be made by, experts. Right? Like this is actually part of what we discussed last time, right? The question whether or not climate change is happening or not should have never been a question, right? That the public discusses. There's certain things that are just like, we need to have a culture whereby we vote for leaders, and there's certain decisions that we trust those leaders to make.
But can we be trusted to vote for educated,
I don't know,
leaders? Well, it's 10:30 now, so maybe we should do the last couple of questions.
Sure. I don't know if there's anything else that,
I have a quick question. How likely do you think we are to use nuclear power as our main source of energy in the future?
Not so likely, in the sense that nuclear power, of course, is great from the perspective of carbon emission, right? I mean, it's a clean form of energy, but at the same time, it's a complicated, nuclear power plant is a complicated thing to build, right? It takes resources to build it, and there's no doubt that if you just were going to say, well, can I just replace my energy budget by trying to change all fossil fuels into nuclear power plants, that's just unworkable. That's just it's just very hard to, you would have to you'd basically have to create like a nuclear power plant every few months or something like this. So it's just not realistic to expect that to happen. I mean, of course, there's also other concerns, but I think the main problem is that it's unclear. I mean, how to make enough of them rapidly enough so that they can actually make a difference. Assuming that you solve all the other problems that people worry about, like toxic, the waste from nuclear power plants and so on. Yeah, I mean, I don't know. We need to do something else about climate. The solution has to be some other type of solution.
Yeah, how about a Manhattan Project on that?
Yeah, exactly. Well,
I think I mean, it just goes to show that people seem to be more riled up when there's a war against other people.
Yeah, to some extent.
Fair enough.
Sure. That's for sure. you know, we still are tribal creatures.
Yeah, I mean, this was awesome. Thank you.
Welcome. My
This was
pleasure.
really great. Thank you for speaking.
Yeah.
Really interesting.
Good night.
Good night.
Thanks, Ami. Thank you. Thank you, Ami. Good to see you. Great talk.
See you, dude.
Bye.
Пока, ребята.
Пока.
Bye. Bye, Lan.
Пока, Линка. Спасибо.
Hi, guys.
Bye.